All right, hello everyone, this is Mr. Crozier, and I'm going to show you how to do this one sample problem here. It is a Riemann sum problem with a given function, and the function is already drawn for us. You could go to Desmos or graph that on a graphing calculator, but here's the function. The function is 0.5 x to the third minus 2x squared plus 8, and that's a cubic function that goes up, then down to the right, and we want to do a right Riemann sum with 6 subintervals. But we're going to do this. We're going to do from -1 to 5. So we're not starting at 0 in this case. Well, first thing we need to do is look where we start and where we stop. And if I put -1 in here, well, -1 is right here. So I'm going to go from there. And if I go to 5, 5 is there. And a lot of times in math what we do is we're going to give this notation. This is A is our starting spot. To B. So we're going from A to B, and we're going to find this area in here. Well, obviously we're going to use Riemann sums because that's our only plan we know now, but we have to divide it up into 6 subintervals, and it may be real obvious how to divide this up, but if we don't know, what we do is we take our B value minus the A value and divide it by the number of intervals. So we have 5 minus -1 divided by 6 is 6 over 6 is 1. Each interval is 1, and you probably were able to figure that in your head, but right there's my 6 intervals, 1, 2, 3, 4, 5, 6. Now sometimes this comes out to be a half. If I would have done this by 6 divided by 12, I would have had a half interval, or maybe I do it 6 divided by 3 and then each interval will be 2, but this is a plan, this is a formula you're going to need. So now that I have this, I have my 6 rectangles. 1, 2, 3, 4, 5, 6. All I have to do is find the area of each one, add them up. It is a right Riemann sum, so the rectangles go from the right side, so I go from the right side over and down. From the right edge over and down. From the right edge over and down, over and down, over from the right edge, and then down, and this one's going to be up above, and from the right edge over and straight down. And now I can color them in, and those are the rectangles I'm going to look at. And this one's going to come out pretty close, I think, because we have some rectangles that have some extra space and some that are missing some space. But just looking at this, I think this is going to come out too high because I have all this extra space here, and I'm only missing a little bit. So I think our answer is going to be an estimation that's too high. All right, so let's find the area. Well, all of the areas, aren't they? They're all 1 by something, so I'm going to go ahead and write that in now. I like to just space it out like this, and every rectangle is a length of 1, right? Let's call this a width of 1. So 1 times something and times the height. But how do I find the height? Well, we don't want to estimate. We don't want to estimate what this height is. I mean, it looks like this is 7.5, so it's somewhere in here, but we're not going to estimate anymore. Not when we have this equation right here. So we can use this to find the output. Well, what is this height? Well, that's the output at 0, right? This is 1 times f of 0, the function's value at 0, because it's on the right side. And what is this one? This one is the function's value at 1. And what is this one? Function's value at 2. What is this one? This is 1 by the function's value at 3. This is the function's value at 4. This is the function's value at 5. So if we know where this is exactly, we can put it right there and just do, I'm going to write this as width times length. Or height is probably a better word here, height. All right, so how do I do that? Well, I just take 0 and plug it in here. And if I plug in 0 here, and here, and here, I just get 8. So this rectangle is 8. This is 8 because it's 1 by 8. Again, don't estimate this when you have an equation. Now here I plug in 1, right? So I plug in 1 there, and 1 there, and 1 there. And again, that's just some computation. If you have your calculator, can't we do it this way? Can't we put in our function, matches, and then go to table, and there's all our outputs. At 0 it's 8. At 1, let's leave this here, at 1, the output is, it's below 7.5, it's 6.5. And here at 2, it's 4. And the output at 3, it's 3.5. And the output here, where are we at now? F of 4 is 8. And the output way up here, and again, that's what we said is that large rectangle. That large rectangle is 1 by 20.5. That's the output there. All right, well, since we're multiplying by 1, we have this very simple, right? This is 6.5, 4, 3.5, 8, and 20.5. There's all our rectangles. All we have to do is add them up. See what we get when we add them up. We have 8 plus 6.5 plus 4 plus 3.5 plus 8 plus 20.5. We have an area of 50.5, and this is again an estimation. There's a way to find it exact that we'll get to later, but it is an estimation here, and I'm probably going to think it's a little bit too high because if you look at this, I think this area right here that's extra, and this area is extra, does more than fill in those gaps right there, and we even have that little bit of extra. So this is probably an overestimation. It's close, but again, how could we make this closer? Now that's the next question we would think. Well, what if we cut it down and we cut these all in half and we did 12 rectangles? Or what if we did 100 rectangles or 1,000 rectangles or maybe even 1,000,000 rectangles? We keep getting closer and closer, and eventually we're going to get to the point where we do, what if we did an infinite number of rectangles? All right, hope this helps you with the Riemann sums. Again, don't estimate these values when you have a function.